we said that V is an additive abelian group, F is a field, and we said that V is a vector space over the field F. If there is a map called scalar multiplication that takes elements from the cross product, say F cross V to V, such that this alpha V is the image of alpha comma V in V, with the properties that alpha times V plus W is alpha V plus alpha W. Second property, alpha plus beta V as alpha V plus beta V. Third, alpha beta V same as alpha times beta V, and 1 from F multiplied to V, that means 1V is same as V. 1 comes from F and alpha betas are from F.
I think
V and W are from the vector space V. The elements of V are called vectors and the elements of F are called scalars. That's what we said. We shall also have this notation that alpha, beta, gamma, delta, and so on, that to present the scalars without mentioning that they are elements of F, and U, V, W, and so on as elements of V, and they are called vectors. And as I also said that we shall be dropping the script V or F or S or addition, multiplication, scalar multiplication, if it is clear from the context. Now, a few simple examples. If one take, then let us take the examples. So suppose we can see that this R over R the vector space. So V is R and F is R. R denotes the set of real numbers, and we can easily verify that this R forms a field. And since it's a field, so with respect to addition, it's an abelian group. So V also can be taken as R. Other properties can easily be verified that makes R as a vector space over R. And for that matter, you can take that this Q, the set of rationals over Q, is also vector space. Now you can see that say R over Q is a vector space. And if we take Q over R, then this is not a vector space. So, for example, to prove that a set has a given algebraic structure, one has to see if all the properties are satisfied. While to claim that this is not so, if there is one property which fails, is good enough. So here we want to see what happens in these two cases as we had seen R over Q. So this here, the scalar multiplication math, if you look, then this is from Q cross R to R, that takes R to, where Q comes from the set of rationals Q and R comes from R. And QR is always a real number. So as far as this property is concerned, here is satisfied. And you can see for other properties also. While the same property here, if you see, you take a field to be R and V as Q, then this should be the map from here to Q. And in that case, we need to see if it happens that RQ defined as RQ, is it a rational number? Is it a rational number? Now, this is not the case if you take, for example, so when R can take, say, 1, and Q you can take as root 2, in that case, this is not so. And therefore, R over Q is a vector space, but Q over R is not a vector space. So this gives me an idea also that let's take let us take say F be a field, then F over F. So V is F and the field is also F. Then this is a vector space. And you can take, since we had already seen this example that R over Q is a vector space. So let us take, say, F and K, the fields, such that one contains the other. So suppose K is bigger, so this contains this. In that case, K becomes a vector space over R. And this as well as may happen that F over K need not be vector space. So likewise, using fields, we can have vector spaces. So another example we can take also again, let us take a set of real numbers, because most generalizations will come from the field of real numbers. So let us take F to be this the field of real numbers, and V, let us take that this is to denote the set of all ordered pairs. Let us say here X, Y, so that X, Y are also numbers. Now here you can define or define two elements. Let us say V1 is X1, Y1, and V2, let us take this is X2, Y2, be in V. So define for this, say V1 is equal to V2 if and only if X1 is equal to X2 and also Y1 is equal to Y2. So number one. Number two, you can define the addition of V1 plus V2 as the ordered pair where the first coordinates are added, Y1 plus Y2. And the third thing that you need to define is the scalar multiplication. So alpha V1 as alpha X1, alpha Y1. So this is for all alpha in F. F is here R. Now you can verify that this V becomes a vector space over F. So R2 is a vector space over R. So R2 over R is a vector. So this gives me the idea that one can have other examples of, let us say, instead of taking R, you could take this Q2 over Q and C2 over C, and you can also have here R2 over Q, C2 over R, and C2 over Q are all vectors. Where Q denotes the field of rationals, R denotes the field of real numbers, and C denotes the field of complex numbers. This makes me state that you can have if K and F are fields, then K square is to denote the set of all ordered pairs, K1, K2 coming from K, and F is a vector space when K contains F. Next, we can have the generalization of, instead of having ordered pairs, we can have triplets, and therefore you can likewise define where you have more such elements. So you can have, say, for example, Rn over R. If you take, say, Rn over R is n tuples. So is, say, here x1, x2, and say xn, where each xi is from R, and any two elements here are said to be equal. So let us take that this is your, say, V, and define here as earlier. So for V as, say, x1, x2, and xn, and W, say, y1, y2, yn in V, where V is Rn. Number one, that this V is equal to W if and only if each xi is equal to yi for every I into n. Number two, how do you add? So the addition is again coordinate wise. So this is, say, u, and what is u? U is x1 plus y1, x2 plus y2, and so on, xn plus yn. And you can also define alpha v, the scalar multiplication, is alpha x1, alpha x2, alpha xn. For all alpha in F, F is here R. So this becomes a vector space. So is a vector space. So if we define the equality of two elements, so sum of two elements and a scalar multiplication here in V over R. So Rn over R becomes a vector space, and naturally this will give me the idea that you can define for this the next example. I don't know which number is it now. So 10, 11, 12 perhaps. So this gives the idea that you can take if F is a field, then Fn over F is a vector space. So there are plenty of examples here that we have generated from well-known fields, but you can also have examples other than them. So let us denote here, say, what is called a polynomial. So let F be a field, and a polynomial, say fx in x over f is an expression of the form fx is equal to, let us take a naught plus a1x plus n1 n xn. N is finite, where the coefficients ai's they come from f. So an expression of this form is called a polynomial over f, and say fx. And if the set of all polynomials of all polynomials, let us say fx here, is to denote the expressions of this form where the coefficients come from f is a vector space over the field f. If we define the equality of two polynomials, if you have fx is a naught plus a1x plus an xn, and gx is b naught plus b1x plus say bm xm. First equality, let me okay. First define for fx, let us say this is aix I is 0 to n, and gx is bj xj is 0 to n. In fx, they call it v. Number one, fx is equal to gx if and only if m and n are equal, and each ai is equal to bi for every I 1 to n. Number two, fx plus gx is say hx, where this is say ck x k a0 to. Now here we depend on whichever is larger. So I write this, say this will go to m or n, whichever is larger. So this is, let us take it here, r, where r is maximum of m or n. And this ck is ak plus for all k 0 to r. So if you define the equality of two polynomials like this, that m and n are equal, and each coefficient of x, each x power is also equal to the other, and their sum is denoted by, say, the polynomial hx, ck, xk, k varies 0 to r, where r is maximum of m and n, and this scalar multiplication is done by multiplying each coefficient by. Third is alpha fx. Alpha fx is where alpha times ai x I by 0 to n. So in that case, this can be seen that this V, which is fx, this becomes a vector space over F. So this V is equal to this fx, the set of all polynomials over F in X, vector space over the field F. Now from here we can have a particular one smaller field, take this 13, can denote the set here, say Vn if you want. So this will be the polynomials say fx in fx, such that the degree of fx is less or where degree means degree fx a0 plus a1x plus say an xn is n if an is not 0. So this consists of all polynomials of degree at most n. Then this becomes a vector space. So you can verify that Vn is a vector space of V. V is fx. Is a vector space over F, and this Vn is contained in V. V is the vector space of all polynomials. However, if you take to denote say Un as the set of all polynomials here in fx, such that degree fx is exactly equal to n, then Un is not a vector space. By the way, the degree of 0 polynomial where each coefficient is 0 is not given. And degree 1 means you have of the form a0 plus a1x. And if it is just a0, then this is called the degree 0. That means they are the scalars. So UN is not a vector space over F that can be seen easily, because if you take fx as a polynomial of degree n in UN, then fx minus fx, which becomes a zero polynomial, is not an element of UN. So this is not a vector space. So there are plenty of examples of vector spaces, and also which are not vectors. We have seen by this time that there are vector spaces which may contain another vector space. So such a situation we have by calling say subspace or vector subspace. So let us take that VFB a vector space, and the W also be a vector space, such that W is contained in V. In that case, W is called a subspace or vector subspace of V. So, for example, we had already seen on the fields that if there is a field, if it is contained in another field, in that case, it is called a subfield. For example, Q is a subfield of R is a subfield of C, Q is also a subfield of C. We had seen that the larger one is a vector space over the small one, and therefore you can see that R over Q, Q over Q. So these are two vector spaces over Q. So Q is a subspace of R over Q. So for example, if K is a field and F is also a field, such that K contains F, then K over F is a vector space, and F over F also vector space. Naturally, here, so if you call this as V and this as W, and W is a subspace. Like that, we had already seen that the set of all polynomials of degree at most n is a vector space over F, and the set of all polynomials in X over F also is a vector space over F. Since Vn is contained in V, so Vn becomes a vector subspace or a subspace of V. So there are plenty of subspaces. Therefore, whenever there are two vector spaces over the same field, one containing the other, the smaller becomes the subspace. Naturally, V is a subspace of V itself, and 0 consists the singleton set consisting of 0 only is always another example of a subspace of every vector space. Naturally, if V and W are two vector spaces such that W is a subspace of V, So W is contained in V. The other thing, when we know by saying this, that elements of W satisfy all the properties of being a vector space over F. And since these elements are also elements of V, and therefore perhaps to prove that this is a subspace, we need not verify all the properties. So one can see that this is a vector space, even if we just verify just one or two simple properties. So we can prove that V and W, the vector spaces, then W is a subspace of V if and only if V contains W and we can see that W is closed with respect to addition and is closed with respect to scalar multiplication. W1 plus W2 is an element of W, and alpha W is an element for every alpha in F. W, W1, W2. If and only if means both sides we have to prove. So suppose we have V and W are two vector spaces, and W is a subspace of V. Naturally, then because W is a vector space in that case, and all these two properties will be satisfied. So conversely, suppose W is a subset of V, which is closed with respect to addition and scalar multiplication, then you need to verify that all other properties are satisfied. This I leave for you because these two conditions can be merged into one. So, or equivalently, you can say that say alpha W1 plus beta W2, this belongs to W for every alpha beta in F and W1 W2 in W. So these two conditions are equivalent. You can take for W1 plus W2 alpha beta as 1, and for this other one also that beta can be 0. In that case, this is simply alpha W. So they imply one another, that these two conditions are equivalent and easily true. Since vector spaces, so we have V as an additive abelian group, and F being a field, F is also an additive abelian group, and non-zero elements also form an abelian group with respect to multiplication. Distributes over addition. So by this time, we have a fairly good idea about the other properties that we have discussed in groups, namely the homomorphisms, isomorphisms, and so on. Of groups, of rings, and of fields we have already studied. That's what I believe. So with this belief, now we extend this same definitions to the homomorphism of vector spaces. So suppose we have two vector spaces, say V and W, and there is a map here from say V to W, then you can call that this is a homomorphism, provided it preserves the addition and scalar multiplication. So what is called is homomorphism of vector spaces. So let us take that V as the vector space over F, and W also another vector space over F, and let us take T is a map from here to here. So it sends an element here V and to V2. Vt is an element of W. So there are two ways of writing this as Vt or Tv. We shall follow this notation as per the Hastings. However, Huffman and Kunze, they use instead of Vt, they will use Tv. So we shall prefer this notation. So this be a map such that preserves addition here. That means if you have V1 plus V2 here, V1 T plus V3, and scalar multiplication. So this means that alpha V alpha times for all alpha in F and for all say V, V1 and V2. So suppose there is a map from the vector space V over F to the vector space W over F, called say T, and the properties T satisfies are that it preserves the sum is V1 plus V2T is V1T plus V2T, and alpha Vt is same as alpha times Vt. Vt is an element of that. Then T is called a homomorph of V to W. Now, this homomorphism, if it is one-to-one, then is called an isomorphism. So, this called an isomorphism of V into W if T is one-to-one. So, his homomorphism and is one-to-one. That means if you have V1T is equal to V2T, then this is implying that V1 is equal to V2. V1T is equal to T, as V1 is equal to V2 for every V1, V2. If it is onto also, if it is onto also, then we say that V is isomorphic onto W, and we will denote this by specify field if you want to write F here, but that is clear, then you need not specify this. So what is a homomorphism? A homomorphism of a vector space V into another vector space W over F is a map which preserves addition and also preserves scalar multiplication. The homomorphism is one-to-one also. We say that this is an isomorphism of V into W. And if the isomorphism is onto, in that case we say the vector space V isomorphic onto the vector space W. Now, as it always happens, there are various equivalent conditions, and using this, we also have the concept what is called as the kernel. So the kernel of a homomorphism T to W, where V and W both are vector spaces over the same field F. So is the set so is the set K kernel of T is the set of all elements here V in V such that V to the image is 0. So what is kernel? It consists of all elements of V, and therefore this is a subset here of all those elements of V which are mapped 0. What one can verify is that if V1 and V2 are in the kernel, observe that for V1, V2 in the kernel, V1T is 0, V2T is also 0, and hence V1 plus V2 of T, this because it is an homomorphism, so this is V1T plus V2T is also 0 plus 0 is 0. And this implies that V1 plus V2 is also in the kernel. And V is in the kernel and alpha is in the field F, then alpha VT, because V is a homomorphism, so this defines that this is same as alpha VT, this is same as alpha times 0, and that you can prove that this is 0. Since alpha 0 is same as alpha 0 plus 0 by distributivity, this is alpha 0 plus alpha 0. So this now these are the two elements here, the additive abelian group, that this 0 for every alpha. Similarly, you can prove that 0 V. That's simple properties that one can prove. So alpha 0 is 0, so that will imply that this kernel. And therefore kernel is a subspace of the vectors. We shall have the notation for subspaces. B by writing like this for subspace. So this K is a subspace. K is a subspace of. So the kernel is a subspace of the domain of the homomorph. Now one can easily establish that the kernel is 0 if and only if the map, the homomorphism is 1 to 1. So you can prove that kernel is 0 if and only if T is 1 to 1. So to prove a homomorphism is an isomorphism, either you prove that the homomorphism is 1 to 1 or you show that the kernel is 0. We shall wind up it here and then again start Friday from onwards. So thank you very much for your kind attention.
Thank you, sir.